time, there were 3 playful little pigs that lived here in this box. They loved to bounce against the wall and sometimes even against each other.
Okay, so now what's going to happen is that I'm going to take a look at just only one gas, right? And take a look at the pressure now. Mr. Tim, do you think the pressure will be higher, lower, or the same as before when all the 3 gases are mixed together?
It should be lower, yeah.
Right? Because there's less gases,
Correct.
it's going to hit against the walls of a container less frequently, right? Yes. Now, if I take a look at just only the second gas,
Okay.
what do you think, Mr. Tim?
Again, it should be lower, yeah.
And of course, if I were to repeat this for the third one, it should always be lower. Now, Mr. Tim, can you run me through, right? Then what is the relationship between the individual pressures of each gas as compared to the combined total pressure then?
Okay, so if I take all these gas particles okay, and I put them back into the box,
Okay.
then the total pressure of the box will just be the pressure of pressure of A plus the pressure of B plus the pressure of C. Okay, and this is what we call Dalton's law of partial pressures.
Okay, then what is a partial pressure, Mr. Tim?
Oh yeah, so the pressure of A is what we call a partial pressure. Okay, the pressure of B is called a partial pressure, and the pressure of C is called a partial pressure. So if I add up all these partials together, all these partial pressures together, you get the total pressure of the
Okay.
box.
So that's going to be the first formula that you're going to learn, right? Now, there's also an alternative way of trying to find out the partial pressure, and I'm going to derive the formula for you, then we can use the formula again, okay? So I'm going to start off with the ideal gas equation, but only for the gas particle A. So I'm going to talk about the partial pressure of A multiplied by the total volume. This is equated to the number of moles of A, and then with a RT over here. Okay. Now, next, I will also set up the ideal gas equation for the total pressure. So PT, the T stands for total. You are occupying the same volume, so the same V over here, but the number of moles will definitely be larger, and you're doing this under the same temperature.
Right.
I've set up 2 different equations. What I'll do over here mathematically is that I'm going to divide the first with the second. And you'll notice that there are going to be certain variables that can be cancelled, and essentially you're going to be left with the relationship between the pressures as well as the number of moles. Now, I'll do a little bit of manipulation over here. You'll realize that you're going to end up with this important equation. The partial pressure of A is going to be given by a fraction of the moles, so therefore I'm going to call this the mole fraction multiplied by the total pressure. Okay, so this formula is going to come in very handy in this chapter as well as subsequent chapters later on. Okay, now can you show us how we're going to apply these formulas in a work example now, Mr. Tim?
Of course. So let's look at this work example. We have a volume of the flask given, 2 dm cubed. So I'm going to write here V, okay? Now it contains 0.2 moles of nitrogen. So we have the number of moles of nitrogen here, right? We have the number of moles of oxygen also given, right? NO2, okay? Now they want us to calculate the total pressure of the flask.
Okay.
So again, you should bring in your ideal gas equation, and that's a very easy PV equals to nRT,
Okay.
right? Your P is your total pressure, and your N is your total number of moles, okay? So what's the total number of moles? I don't care what these gases are. I know it's N2, I know it's O2, but my total moles is just number of moles of A plus number of moles of B, okay? So that's 0.6 in this case. So
you must make sure that you're not reacting as well, right?
exactly, right? They need to be inert. They don't react with each other.
Okay.
Now, again, please be very careful here. When you're using the ideal gas equation, all units must be
SI units.
yes, okay? So you got to be careful. I need to convert the volume dm cube into meter cube, divide by 1,000, okay? Make sure that your temperature, again, is in kelvins, all right? This is lovely because you have told us kelvins. So it's there. Now, so from here, your R is always 8.31. I'm sure you guys know this, okay? And then we put everything in, calculator pressing, and then you get 9.97 times 10 to the power of 5, not ATM, pascals, okay? The SI units, pascals, all right? Now, next, we're going to have partial pressure of nitrogen, and like what Mr. Long mentioned to us just now, we're just going to use the partial pressure formula, okay? So take a look. I'm going to bring this down. The partial pressure of N2 is just the mole fraction of N2 multiplied by the total pressure, okay? So plug this in again. What's my number of moles of N2, Mr. Long?
0.2 mole.
Yeah, total number of moles?
0.6.
Yeah, okay. So we multiply by the total pressure that we got in part A, plug that in, and we found the partial pressure of N2.
Okay.
Now I'm also going to do this for the partial pressure of oxygen in part C. Partial pressure of O2 is the mole fraction of O2, right? Multiplied by the total pressure. Okay.
Okay, so this is actually quite a long method.
Yeah.
So there's an alternative method which is to use the Dalton's law of partial pressure, right? And that's going to be given over here. You tell me that the total pressure is going to be the addition of their partial pressures. So since I part B, I already got the partial pressure of N2. It's not that hard for you to find the partial pressure of O2 anymore.
Smart.
Okay.
Yes. Hey, Mr. Leong, how's your day?
I'm fine. So what we saw earlier is an example of a real gas. But in ideal gases, right, these particles are not supposed to interact with each other. So in terms of chemistry, we are saying that they're not supposed to have any intermolecular forces of attraction. And that is going to be one of the assumptions of an ideal gas. Now, in general, there are 5 of them. Okay, I've introduced the second one over here, which is the fact that your gas particles have negligible intermolecular forces of attraction. Okay, the other one that's important is actually look at the first one. Now we say that these gas particles, right, they are going to have negligible molecular volume. Okay, now this is different from the volume of a container. We're just looking at the particle itself and seeing what kind of volume it occupies. For ideal gases, they are just going to occur as one speck of a point. Okay.
Okay, and there are also 3 other assumptions that you must know. The next one is that the gas particles are in continuously random motion.
Okay, thank you.
Okay, now not only that, the collisions are perfectly elastic. Now what this means is that when they bump, they do not stick. Right? They bump and then they break free. Okay, and the last but not least, we have the average Ke that's actually proportional to temperature. Now average Ke means this: Ke1 of this particle plus Ke2 divided by the total particles, which is 2 in this case. That is average Ke, and it's proportional to the temperature of the box that they're in. Okay.
But in reality, right, you realize that these gases are never ideal. Right. So you're far from ideality. Why is that so? Is because they violate the first 2 assumptions of our ideal gas. So in general, the first 2 assumptions are the ones that's most closely related to chemistry. Right. Now, in reality, we understood that the gas particles, they do occupy certain volume. There's just a small volume over here, so it's trying to violate our first assumption over here. And also the fact that everybody knows that every gas is going to exhibit a little bit of intermolecular forces of attraction, right? So that's going to violate our assumption number 2 over here. All right. Now, since real gases deviates from ideality, are there any scenarios for us to make our real gases behave more ideally? So if let's say, Mr. Tim, if I have to ask you, if you want to find a perfect ideal soulmate, right? What should you do?
Well, then you need to make sure that you don't give her so much pressure, right? You need to give her a stress-free environment, him or her, up to you. Right? You need to give her a stress-free environment.
So in the context of chemistry, right, it means that we are trying to introduce low pressure. Now, why is that good? It's because low pressure always corresponds to large volume. Now, what's the significance of that? You tell me that actually the molecular volume of the particles is now going to be insignificant as compared to the volume of the entire container. These particles are very far apart. There's a lot of empty spaces in between them. And that is why this particular condition is helping me to go closer towards the first assumption. That the fact that the molecular volume is going to be insignificant as compared to the volume of the container. Okay. Now, what else would you do, Mr. Tim, to attract your ideal soulmate?
I will try my best to look very, very hot.
Okay. You mean exercise more, build up muscles like yourself?
Yes.
Okay. So in the context of our chemistry, we are trying to increase the temperature as high as possible. Now, why does that work? It's because you're going to introduce kinetic energy. The particles will possess sufficient energy to overcome their intermolecular forces of attraction, right? And that is going to be going closer towards my assumption 2, where you're going to see negligible IMF. Okay. So, Mr. Tim, can you bring us through the next part?
All right. Now, so for the next part, it looks very, very scary. We won't be doing this here. We'll be taking it to class, right? When our lovely tutors will explain to you the graphical representation of how real gases deviate from ideality. Okay? Goodbye.